All right, our next speaker is Lauren, and Lauren is going to present us PSym, efficient symbolic exploration of distributed system. So Lauren, the stage is yours.
Hi, so today I'll be talking about how to scale exploration of distributed systems behavior, and this is joint work with Ankush, Desai, and Aarti, Gupta. So in distributed systems, we have several nodes, each of which runs its own computation, and these nodes can communicate with each other by sending messages. We're going to refer to the receive and processing of a message as an event, and we can give these events names so that we can easily refer to them. So at this point, we can ask, what is the behavior of this system? Well, there are several possible interleavings of the events, so we get several possible behaviors. In general, for distributed systems, we have a combinatorial explosion of possible behaviors in the system. And for a simple example with only 6 messages, if you're interested, you can see more details about this example in the paper. We already have an execution tree that looks like this. So here, every node is a state, every edge is a transition, and we also label every transition with its associated event. So this combinatorial explosion poses a scalability challenge if we're trying to explore everything in this execution tree. So what do we do? Well, one thing we can try is use partial order reduction. So this has been the focus of a lot of work over the years. And if we do that, we can avoid exploring redundant interleavings of events in the system. So if we do that for this example, we can avoid exploring all the parts now shown in red. Another thing we can do is use state caching, which has been used by model checkers like Spin and TLC. And with state caching, we cache states as we explore them, so if we revisit a state, we're not going to do re-exploration from it. So if we do that for this example tree, then we can avoid exploring the parts now shown in blue. So both of these techniques identify redundancies in the system, but these aren't the only redundancies. And we can see this more clearly if we take a less monolithic view of states and transitions. So let's consider these 2 transitions, and in particular, let's look at the computation steps in order to perform them. If we do that, we can actually see that, hey, some of these are the same. So these transitions have overlapping parts of their computations. And this kind of thing is actually common in distributed systems, especially if you take a macro step view of them like we're doing here, where every transition is just a single node that processes a message, updates its local state, and maybe sends some messages. So the key idea in this work is that we should try to avoid doing this redundant computation when we have transitions that overlap like this. And if we do that for this example, then for all of the transitions now shown in orange, we don't need to separately compute these transitions because they overlap with others in the system. So if we do this kind of thing and use the key idea that I just described, this can really help us scale exploration. And to convince you of this fact and give you an idea of how much this helps, I'll give you a small preview of our experimental results. So we implemented this idea in a tool called Psym that can be used to check distributed systems that are implemented in the P programming language. And when we compared Psym against the state-of-the-art model checker TLC, it achieved a speedup of 2.5 times on average on a set of open source TLA plus benchmarks. We are also able to apply Psym to real-world benchmarks, and in particular, we verified 4 industrial-scale distributed protocols that are in use at Amazon Web Services. So hopefully I've convinced you of the merits of exploiting overlapping transitions in this way. So in the rest of the talk, I will describe first an efficient state representation that lets us efficiently identify when we have overlapping transitions. Then I'll talk about the exploration algorithm that actually uses this state representation to avoid doing redundant computations when we have overlapping transitions. And then finally, I'll talk about the benefits of using overlapping transitions this way, as shown in our experimental evaluation. So as mentioned, first I'll talk about the state representation. So in order to recognize when we have overlapping transitions, we need to know that relevant parts of states and updates in the system are the same. This leads us to have the following requirements on the state representation. First, we need that it is fine-grained so that we can actually inspect parts of the states. Second, we need that it is canonical, so that when we're checking that parts of the states are the same, this amounts to a simple and efficient syntactic check. And finally, we need that this captures all of the non-deterministic choices in the system, because we're trying to explore all of the behaviors in the system. So I'll talk about each of these in turn, starting from the bottom. So first, let's talk about how scheduling control input guards are used to capture these non-deterministic choices. So scheduling control input, or SCI guards, are just Boolean formulas or guards that we introduce per option, per non-deterministic choice that we have in the system. And this is for all kinds of non-determinism, be it scheduling non-determinism, control flow non-determinism, or input non-determinism. And what we have is that per choice, we'll introduce distinct guards for every option in that choice. Meaning that if we look at any two options for a choice and look at their guards and take the conjunction, then that's going to be false. So let's look at what that looks like on an example execution tree. So our first choice isn't really a choice because we only have one option. So the associated Boolean formula here is just going to be true. At the next choice, we have 3 options. And in order to have distinct guards for each of these 3 options, we're going to need at least 2 Boolean variables. So we introduced 2 fresh Boolean variables, G0 and G1, and use these to construct our distinct guards. So for example, here we might have G0 and G1, here G0 and not G1, and here not G0. And we can do this for the rest of the execution tree. And the idea is that if we take the conjunction of guards along the path to a state, then this will identify all of the choices that we made to get to that state. So for example, we can consider this state and the path to it, and take the conjunction of the guards on the path, and this gives us the SCI guard for this state. And what we have is that we have distinct guards for every path in the execution tree. So if we take any 2 states, and they're in different paths in the execution tree, and we look at their SCI guards, the conjunction of those guards will be false. So now let's talk about how we get a canonical representation by using value summaries. So primitive value summaries were initially introduced as just value summaries in the multi-SE work by Sen and collaborators. And these are a way of representing values under different control flow as a sets of guarded values. So let's look at what that is like on an example. Let's say that we have this variable x that takes value 1 under path condition g and 2 under path condition not g. Then a primitive value summary for x would look like this. Now, in the initial setting where these were used, this was for symbolic execution of sequential programs, so the setting is different from ours. And in our setting, instead of path conditions, we are going to have SCI guards. But the rest of the idea is the same. And this representation is canonical because, well, we use binary decision diagrams to represent the guards, so those are canonical. We disallow false guards, so if we do an operation on value summaries and get a guard that's false, then in order to maintain our canonicity invariant, we're just going to remove the offending guarded value. And then we also disallow duplicate values. So again, if we ever have that, then we will combine the offending guarded values by taking the disjunction of their guards. So now let's talk about how we get a fine-grained state representation. And we do this, to do this, we propose using composite value summaries. So primitive value summaries value components are monolithic. So if we consider a tuple, for example, and its primitive value summary, we can see that the value components of the guarded values are themselves entire tuples. If we use composite value summaries instead, we can get a finer-grained representation. So for every component in the tuple, we can then have a separate value summary, like this, and then the composite value summary for the tuple is then a tuple of these. So we can do this kind of thing and represent using composite value summaries not only tuples, but also lists, maps, and other composite data structures. But importantly, we need to make sure that we maintain the invariance that we need for canonicity. And this is because we're going to be performing operations on them, so we don't want to break canonicity as we do that. And I won't go into the operations that we perform on composite value summaries much here in this talk, but I do want to bring up this one merging operation, which is what lets us identify when we have that state components are the same. So now I'd like to talk about the exploration algorithm. So we're going to proceed in a breadth-first manner. So if this is our execution tree, where we've labeled the transitions with their SCI guards, then we're going to be considering a frontier of states. And what we'll do is represent this frontier as a composite value summary of the states in it. So let's say that one state is this, where our set of pending messages is just this one ping message with payload 1 to a target node, and here's the local state of the target node. And let's say we also have this other state in our frontier, which is the same as the first state, except our ping message now has payload 2. So the composite value summary that we use to represent the frontier is this. So here we can see that the states components occur under their respective SCI guards in this composite value summary. So now how do we compute the next frontier? Well, what we'll do is lift all of the computations that we normally do in order to advance a single state along a transition to work over value summaries of states instead of just states. And, well, our frontier is a composite value summary of states. So to get the next frontier, we just apply this lifted next state computation to the frontier. So now let's look at how this works and in more detail and link this back to overlapping transitions. So here's our frontier, and we want to compute the next frontier. And in our system, we have it such that whenever a ping message is received by this target node, the target node will run this bit of code, which updates its local state, this local count variable, and does some other unrelated stuff. So if we look at the frontier representation, we can actually see that it has already merged the relevant parts of the states. So that means that regardless of what state we are in the frontier, we are definitely going to be executing this bit of code. So when we compute the next frontier, the lifted version of this bit of code is run once, and in particular, things like this update, this increment of this count variable, that's performed only once as a shared computation for all of the transitions from the frontier. So now I'll talk about the experimental evaluation. So as I mentioned, we implemented our technique in a tool called Psym that we can use to check programs in P. And our technique is compatible with partial order and other reductions, as well as abstractions and fixed point detection. So first, let's look at the results when we ran Psym and compared against TLC, which is the model checker for TLA+, on 10 benchmarks that are based on a set of open source TLA+ benchmarks that we ported to P as needed so that Psym could handle them. So before I actually present the results, I would like to note that TLC uses state caching via hashing, so it's not going to re-explore from states that it revisits. Psym, meanwhile, uses the techniques I just described, so it doesn't do state caching at present, but because of the frontier representation, what it will do is merge all of the states in a frontier. So we ran both of these tools per benchmark with a 15-minute timeout and got results that look like this. As you can maybe see in the blue, Psym solved 9 out of 10 of these benchmarks faster than TLC. And for 2 of these 9 benchmarks, TLC actually timed out. For the remaining 1 benchmark, the tools had similar performance. And just looking at the benchmarks for which TLC didn't time out, Psym had an average of a 2.5 times speed up over TLC. So now let's look at the results that we got when we tried to apply Psym to real-world distributed protocols. So when we applied Psym to distributed protocols used at Amazon Web Services, we got these results. So to give you an idea of the scale of these guys, we can look here and see that there are about 1,000 lines of P code and had from 13 to 22 concurrently running nodes. And just using Psym, we were able to verify all of these protocols. And if we combine Psym with other reductions, then we can achieve a scalability improvement. So in particular, we combined Psym with reductions based on Lipton's left movers, as shown by the L here, and also reductions based on symmetries, as shown by this S. We also ran Psym on, and were able to verify 6 P benchmarks that were used in previous work on P. And we also applied Psym to 2 parameterizable infinite state benchmarks which Psym was able to verify by using a combination of predicate abstraction and fixed point detection. So that brings me to the end of my talk. So I'll give you some takeaways. We've seen that we can use composite value summaries to represent distributed system states. And doing this lets us recognize when we have overlapping transitions, which we can then use to avoid redundant computation. If we do this, then we can scale systematic exploration to be able to handle industrial scale protocols. And if we further combine this with abstraction and fixed point detection, we can handle infinite state systems as well. As future work, we would like to explore better abstraction techniques because so far we've only considered predicate abstraction. Thanks.
All right, remember that we have a microphone in the middle of the room, so if you have any questions, just move here and to the microphone. Okay, so I have a question that maybe I'm missing in the talk, but what type of properties are you trying to verify for these protocols?
Right, so mostly we looked at safety properties. So in P programs, you can write asserts. These will also check things like if you have like runtime errors in P, this will also check for that.
Okay.
Tim, Princeton, did you look at all at how varying the number of actors or elements in the distributed protocol could affect verification?
Yeah, so as you increase the number of P machines or nodes or whatever, then it's, your state space increases, so verification takes longer. Some of the TLA plus benchmarks, if I go back, are actually the same benchmark with different parameters. So you can see, like, for the HLC, the logical clocks benchmark, it takes longer as you increase this max T parameter.
Thanks.
Any other questions? So you mentioned that your approach is also compatible with other approaches such as partial order reductions. I wonder if you have tried combining this in any of your evaluations and how would they perform by combining them together?
Yeah, so, well, I mentioned these reductions based on left movers and symmetries. We've also done actually, we have a partial order reduction that's sort of enabled by default in our tool, and that seems to help a lot. And we also tried some other kinds of partial order reductions, like monotonic partial order reduction, and that seemed to help a lot too. A lot of these depend on the system that you're running on, so obviously, like, symmetries don't help if you don't have any symmetries in your system. So that's sort of a case-by-case basis.
I see.
Yeah.
Yeah. All right. Let's thank our speaker again.